I sent an email, again, for virtual people, probably more than the in-class people. I sent an email out with a handout attached, and then I screwed up and it was already filled out, and then I sent a new one. The filled out one is fine, but we'll go through most of that exactly or similar to what it's filled out as. I'll post a filled out version of my notes anyway. But there is actually a difference between the filled out version that I posted and like the new version, the blank version. So I'll post a filled out version of like the updated. So there were some changes made between years. So I think the filled out one that I sent out is like last year's version of this. So it's filled out from then. So there are some changes in this one. I think the filled out one, you don't get the little dino in the airplane. He's my favorite. So for the quiz, just to start, I guess I can start with. I'm already recording. Cool. Well, hi, future people who are going to watch this. So for the quiz people did really well. Hopefully, if you didn't do as well as you would have hoped, this is a good, relatively low point total way to say, oh, I maybe don't understand these as well as I think I would. This was a fairly involved problem. You had to handle pressures and velocities and all of these things all together. So sign conventions were people tripped up on. Making sure that pressure is acting on both sides because you had a pressure on both sides. One was an atmospheric pressure. Making sure you get all the directions right. I think a number of people, what I do, especially for pressure, just remember like pressure pushes in on a surface. So I drew my arrows first and then said, okay, so I know on the left-hand side, that has to be positive because it's pushing in. So it's pushing positive X. On the right-hand side, it's negative because it's pushing in, which is negative X. So you can use some of these tricks to help you get sign conventions right. And then most of the other stuff was like, the usual, like people messed up units or plugged things in their calculator wrong or kind of minor things like that. But I thought people did really well. You people did really well, not just some random people. It was you guys. You did well. And so I was happy with it. Hopefully, this is a good kind of check for you personally with, what did I mess up that I don't want to mess up later on the exam on these kind of problems. So that was the goal of it. To talk a little bit more about the exam, I sent an email out earlier today giving kind of a point by point, like these are the chapters and sections that are going to be on the exam. Most of the exam is going to be chapter 4 stuff. We didn't cover all of chapter 4, right? So if you go and write down everything from chapter 4, like we didn't cover that. So you're going to have lots of stuff that is just there to throw you for a loop. So I tried to point out in my email, like what specifically we covered and what we didn't cover in chapter 4. Obviously going back to the homeworks is a good spot to start. The one thing, I made mention of this in my email, but one thing that is in chapter 4 that we never touched is this thing called Bernoulli's equation. Don't write Bernoulli's equation. Don't do it. Leave that off of your thing. We didn't do it. It won't be on the exam, I promise. We will do Bernoulli's equation fairly soon, but not yet. So don't write that down because it will just mess you up. So most of the exam, I would say somewhere between like 2/3, maybe to 3/4, somewhere around there of like the time and the points are going to be chapter 4 things. So what does that mean? That's broadly speaking what I would call Reynolds transport theorem, but it's conservation of mass or momentum on a like F equals ma on a control volume. So these are the fluids coming in, fluids going out, and we're finding forces, or we have so like fluids coming in, fluids coming out, we're finding forces in the system, we're finding forces that the fluid is pushing on something like this quiz. You're finding like the propulsion of the jet boat. It's those kind of problems. The conservation of mass problems, there could be something, they're going to be built into the momentum problems. So if you're finding forces, you often are finding conservation of mass stuff along with that. So you're often using those together. There will be one problem that is conservation of mass all alone by itself, probably. So that would be obviously more exciting than like Q1 A1 or Q1 equals Q2, right? It's going to be that, but there will be something more involved in it. Most of the problems, almost all of the stuff that we've done has been a uniform velocity profile, so that we've been able to do, and you guys all did this right on this quiz, so look at your quiz and you can remember what I'm talking about. We have this integral over the control surface of velocity, density, velocity dotted with area, like that integral. When we have uniform velocity, that flips to a sum. There will be at least one problem on the exam where all of it or part of it will be non-uniform velocity profiles. So you actually have to go through and do that integral. There are a couple places that we've done that. There was one problem in the homework where you had to calculate the mass flow rate, the momentum flux, and the kinetic energy flux through a pipe, like given, remember that one? We had to do a whole bunch of integrals. So there's one problem like that. I will promise you that you will not have to do kinetic energy, but you might do either mass or momentum. There could be like a mass flow rate. So the other mass flow rate one, the example that we did in class was you had uniform velocity coming in, and then you knew farther down the pipe the velocity was parabolic, and you knew what the equation was, and you said, how are the two things related? So it could be something like that. There was, I think, another one in the homework where like it was a kind of funky shaped bend thing, and like the velocity was coming in and it was linear at an angle, and then it went out two places. That was, it could be something like that. So the thing to make sure that you have written on your equation sheet, or that you just have memorized, I guess, would be what is a differential area in different coordinate systems. So either in Cartesian coordinate systems, right, where a differential area is like a differential height times the width, or in cylindrical coordinates where a differential area is that little like donut shape, which is like 2 pi r dr. But go back and look at some of those examples and make sure that you know how to do, how to actually handle the integrals. So that will be not a large part of the exam, but that will at least show up in one place. Let me think. I guess the other comment about the chapter 4 part of the exam, there will not be an accelerating control volume on the exam. So we did an example in class. We did an example on the homework. It will not be on the exam. So there could be a moving control volume, but there will be like moving constant velocity, like an inertial control volume, like what. So there won't be an accelerating one. So I wanted to make sure like we get a chance to talk about it, see a little bit how that works in practice in the homework, but that's not going to be on the exam. I guess the other thing to comment, I would say exam questions are not questions like question 3 of the homework 5 that are questions about how well do you remember your algebra. So a question like that I don't think would be a particularly good exam question, because that 50% of the problem is algebra, probably. But I like that question because I think hydraulic jumps are cool. And also it's interesting to see how they work kind of as from a momentum standpoint, I think at least. But yeah, so it'll be this quiz I think maybe gives you a good idea of, so we have like 20 minutes to solve this problem. If I gave you a similar problem, I would expect about a similar kind of time for it, 15 to 20 minutes. So that's kind of the timing, right? I'm not going to give you one problem for the whole exam. The other part of the exam, so most of it's going to be this kind of stuff, chapter 4. The other part of it is going to be chapter 5 stuff, which is stuff from this most recent homework. Chapter 5 has a lot of stuff in it, so obviously it's not going to be all of chapter 5, but it's going to be, I think it's 5.1 and 5.2, but don't quote me on that. Look at the email that I sent out that you can quote that. But it's going to be the same type of stuff. So, you know, having to use the differential continuity equation to figure out, like, you know, does this velocity field break conservation of mass or not? And looking at the stream function and maybe using stream function to find flow rate like you guys did. So basically the stuff that you did in this last in-class thing, those same kinds of things. So that will be the chapter 5. Okay, the chapter 5 portion of it. So yeah, if you have questions as you're looking over stuff, the exam's Wednesday, shoot me an email. I'll try to respond to everybody. Hopefully the email I sent out earlier gives you kind of a point-by-point thing so you know what places to look and what to study as you're going through that. I don't think I'm forgetting anything. Am I forgetting anything? I don't think so. So that's why I sent out an email, because then I can think about it and actually have stuff clear. But if you have questions, shoot me an email, let me know. We can talk about stuff more on Monday or by email, and I can send an email out to everybody, kind of whatever, if anything comes up. Okay. All right. So if you want to take out the handout thing or open it up on your computer or somehow have it, if you're taking this virtually and have this opened up, I'm going to put my completed version. I'll post that. So if there's, like, you can't print it or you can't find a way to take notes, don't fret. The completed version will be posted. And we won't do too much with all of the details of this outside of, like, going through some of the details. So if you miss some of it, it's not the world's biggest deal. But what we're going to be doing today and maybe all of Monday, I don't know, we'll see how far. We'll finish it Monday, finish this discussion, not all of Monday, half of Monday, something like that. We're going to look at fluid motion. And we're going to go into all of its lovely, gory mathematical differential equation detail. And it's going to be, okay, I want to go into it in detail because it is really the foundational. If you ever run across a fluid model, if you're modeling, you know, aerodynamics, if you're modeling what does fluid flow look like in this situation, if you ever run across a fluid model, like, this is what you did. This is what your fluid model is based on. So if you go, you know, and you're looking at, like, computational aerodynamics of some car, like, what are you actually doing? You're doing exactly this. Like, this is what all of that is based on. So I think it's worth going through in the detail, because otherwise it's just, if you flip over to the very last page, you'll see what our answer is. And it's big and it's ugly, and there are 4 coupled partial differential equations in 4 dimensions, and it's gross. But those are the equations that you solve, right? So it gets really exciting. So we're not going to spend too much time actually solving those. We'll do a little bit, but typically how those equations are solved in real life is computationally, right? You solve them in a computer model, which is why we're not going to really solve them by hand too much, other than to, like, see a little bit how that happens. But the cool thing is, we can, without too much work, we can see, like, where those guys come from and what why they look the ugly, big, nasty way that they look. So that's what we're going to do over the next 2 days, is we're going to dig into a little bit where these things come from, because I think it helps us understand better where, if you ever use a computer model, it'll help you understand better where that comes from and why it works the way that it does. What exactly is it doing? So I think there's a lot of value there. The other thing, too, is I think you have to, if you take fluid mechanics, you have to see these equations. These are the, okay, there's one other equation that maybe is in, you know, like neck and neck in the most famous equation in fluid mechanics. It's either these equations, the Navier-Stokes equations, or it's the Bernoulli equation. We haven't done either of these yet. We'll do Bernoulli next, but first we'll do the Navier-Stokes equation. So if you've taken fluid mechanics and somebody goes, oh, the Navier-Stokes equation, you'll be like, ah, yes, and now you can nod knowingly after this. Right, so this is like half of having taken classes is like, you know, talking about, like if you took organic chemistry and like you meet somebody else that took organic chemistry, you're like, ah, yes, organic. This is like half of what. So fluids, you'd be like, ah, the Navier-Stokes equation. I didn't really do much with that, but I've heard the name and we can both nod about it, right? You can commiserate and be like one of the crew. So, all right, so that's what we're gonna build. We're gonna build the Navier-Stokes equations. What we're really trying to do is this, right? We're trying to do high school physics, but on a fluid, which makes it more fun. All we're trying to do is F equals ma. That's why things move. They move because of forces. They change velocity because of forces. The problem is with fluids, things get messy. So if you think of, okay, what are 4 components of a fluid's motion? So they can translate, they can, like if you look at a fluid particle, that's what we're going to be tracking. And so we're going to have to change our perspective a little bit for this discussion. We are going to be the fluid particle moving in our flow. So you can translate, you can move from point A to point B. You could also rotate, right? Just like any solid body, right? You can be translating, you can be rotating. The difference with fluids is you can also experience linear deformation or angular deformation. Okay, so what do I mean by linear deformation and angular deformation? This is, you as a fluid particle could be squished, or you could be squashed. These are the technical terms, of course. We only learn the technical terms. So, right, you can get, because you're not a solid, you can be like squeezed and squished and have all kinds of different deformations that a solid body wouldn't have. So this is why fluids get a little bit more complicated than solids, and why we don't have the same big nasty set of equations for solids that we have for fluids. We're not going to really talk too much about those deformations, which is why I don't care if you think of it just as like we can translate, we can rotate, we can be squished and squashed. Like that's good. Okay, so what we're going to start with is talking about acceleration. So we're going to build up F equals ma by looking at each of these components. We'll look at acceleration first, then we'll look at mass, then we'll look at forces. So first off, we want to start, what does acceleration look like for our fluid particle? And we'll start off with a question. So think about a steady state flow, which is most of the systems that we've talked about. So a steady state flow, that's true by definition. The change in the velocity field with time is equal to 0. So by definition, velocity field's not changing with time. That's why we call it steady state. What about the acceleration of you as an individual fluid particle? Are you accelerating or are you not accelerating? Okay, so think of this example. So I am a firefighter. I'm not actually, I just wish I was that cool. But so somebody else who's cooler than me is a firefighter and is holding a fire hose and spraying it at a wall. Okay, and they're holding it steady. And nobody's like opening or closing the valve, so it's just like a steady state thing. And they're shooting the fire hose, holding it at the wall. You are a fluid particle in that system. Imagine your trip. Like, where do you go? Do you accelerate? Do you decelerate? Do you experience a change in direction? Absolutely yes, right? So this is where this discussion gets a little bit weird. We have to be thinking in two different like worlds at the same time. So we have to be thinking both as like, how is the overall picture changing? Like the fireman is standing there, he's holding his fire hose, he's not moving. Everything is what we would call steady flow. It's not changing with time. The velocity field is not changing with time, the whole picture. We have to be able to think about that, but then also, what about you personally as a fluid particle moving in that system, right? You start by going slowly in the hose, and then you go through the nozzle and you speed up and you get shot through the air, and then you crash into the wall and come to a stop or fall down to the ground, and then you form a puddle, right? So your journey, you might have a lot of acceleration, but the whole flow is not changing. So we're going to have to be kind of living in both of these two worlds at once. And what we're trying to do is we need to kind of connect these two worlds of the whole flow by itself, but also like you as a particle. Okay, your particle, you definitely are, it can be accelerating. It doesn't mean that you always are, but you could be. So think about water going through a nozzle, right? It's going to be, the whole system might not be changing, but certainly like the water going through that nozzle is going to be accelerating and it gets shot out the end. So okay. All right, so we're going to be looking, we want to find F equals ma for an individual fluid particle. So what is the acceleration of a particle? Well, it's going to be the change in the velocity of that particle with time. That's just the definition. So we'll first write this. So acceleration of our particle is equal to the change in the velocity of the particle d time. Okay, and this is how we're going to start to connect these two. So if we took a snapshot at a given instant in time, what is the velocity of the particle? So at a given instant in time, the particle is equal to v x particle, y particle, z particle, and t. So what do I mean by that? So again, if you're thinking about like this fire hose example, if I took a picture of you somewhere, your velocity at the instant I took that picture is equal to the velocity field at the position that you happen to be in. So if the velocity, like right at the end of the nozzle, is 20 meters per second, and I take a picture and you happen to be right at the end of the nozzle, you're going 20 meters per second. If I take a picture a little bit later and you're in a puddle on the ground, the velocity at that spot is 0. So I know you're in the puddle on the ground, your velocity is 0 because that's the value of the velocity there. So at any given time, I can take a picture and say, you're right there. I know your velocity. It's the value of the velocity field. Okay, so let's write out, so this is the value of the velocity field at time t and the location of the particle. So your velocity as a particle is equal to the velocity where you happen to be sitting whenever we find you. So let's think about how you move, because that's obviously like a key part of acceleration. How are you moving? So if you as the particle are moving, we'll look at a differential velocity. You could be moving in the x direction, you could be moving in the y direction, you could be moving in the z direction, and it could be changing in time, right? You could be changing in all of these dimensions. We're gonna, for now, assume that we could have a flow that's changing with time, like not necessarily a steady flow. So your differential particle velocity, I'll write this and then we'll try to talk through a little bit why it looks the way that it does. Plus d dy particle plus dv dz particle plus dv dt times dt. Okay, so what are all these different terms? So if we moved from, say, like just before the nozzle to a little bit into the nozzle, we would experience an acceleration, like as we start to go out the nozzle. What would that be? So it would be equal to like how far we moved. If we moved from just outside the nozzle to just inside the nozzle, how far did we actually move? That's what this part is. So this is how far in x, and then obviously the same in y and in z, and how much time elapsed in t. So how far did the particle move, or the distance that moved in x, y, and z. So the change in velocity, again, as you're moving in this velocity field, it matters like how far did you move in any direction. And then the second part is how fast the velocity is changing in all of those directions, how fast the velocity field is changing. So if you know how far you moved, I moved a centimeter, and you know that over the distance of a centimeter, this is how much the velocity changes. Then you can back out how much your velocity changed. So this is how the velocity field is changing in x. Okay, maybe it's easiest to think about the last term, the change in time one. So if you knew that, say, somebody's turning on the fire hose and the velocity is changing 1 foot per second every second, because as somebody's opening the valve, and you said, okay, you took a picture and then you took a picture 1 second later. But 1 second later, that's dt. the dv dt part, it's changing 1 foot per second per second. So you want to figure out, okay, so then you just multiply the two, and you know my velocity changed 1 foot per second over the course of that second. So that's all that we're saying here. We'll look a little bit more at this in a second. So that's a differential velocity. If we want to look at acceleration, acceleration is just change in velocity with time. So an acceleration of our particle, I'm just putting a subscript p instead of writing particle because it's shorter. But acceleration of our particle is equal to, well, the time derivative of this, right, is dv particle dt. So all I'm going to do is take this equation above and do the differential of it with respect to time. Put a dt on the bottom of each of one of those terms. So this is equal to partial v, partial x, and then I'll put a dxp on top and dt on the bottom. Okay, and we'll keep doing that. dv, dy, dyp, dt, plus dv, dz, dz particle dt, plus dv, dt, dt, dt. Those are supposed to be the same dt's. dt. Okay. Okay, so a couple things. The first thing that we can see, this guy, the dt and the dt, that's just going to go to 1, dt over dt. The more interesting things are what happens with these terms. So this term, and this term, and this term. What are those? Velocity of what? It's a change in position with time, but it's a change in, what's my little subscript? Particle. So it's how fast is that fluid particle moving. This is the definition of the fluid particle's velocity. So okay, the change in position with time, that's velocity. That's the definition of velocity. The cool part is, let's think about that. What velocity is that? So it's the velocity of your fluid particle. But we said that's the same thing at like a given instant of time. Right, what we just said is that at some given instant, the particle's velocity is wherever it happens to be in the velocity field. So if I want to know the particle's velocity in the x direction at a given moment in time, that's little u. That's the x component of the velocity field at that location. So we can rewrite this. This is like u. That's the u component of the x component of the velocity. Again, at that position. So let's rewrite this. So we can rewrite this equation. That's by definition u. Get blue so I'm consistent. So the acceleration of our particle equals partial v partial x u plus partial v partial y little v plus partial v partial z little w plus dv dt. Okay, so this is kind of a weird equation, but let's think a little bit about what we just did. So we connected, through this equation, we connected how a particle accelerates, the acceleration of a particle, that's the left-hand side. We connected that to things that only have to do with the whole flow itself, the velocity field. So we have kind of these two different perspectives. We have the perspective of U as this little particle, but then the bigger picture of the velocity field. This is how they're connected. We're going to define this kind of weird notation. We'll talk about it in a second. But we'll write this as capital D V dt. And again, I'll define that in a second. Just live with the weird notation for right now. We kind of have, if you look at the right-hand side of the equation, the dv dx u, dv dy v, if you look at that part, there are clearly like two different things. So there's this whole first part, which we call convective. Convective flow. So this is change in the particle because of flow or because of movement in the velocity field. So again, if you're thinking about the fire hose example, you as the particle, you're going to experience a change in velocity and acceleration as you move from inside the hose through the nozzle and crash into the wall. You're going to have a lot of different accelerations. So you're going to have accelerations based on where you are. That's what this first convective flow terms. That's what that is. You could also have accelerations because somebody's turning on the valve and increasing the flow rate, or turning it off and everything's slowing down. So that's what this last term is. This is local acceleration. So this would be like changes to the whole velocity field, changes to v. So there are these two separate parts. Okay, so convective flow, changes in particle velocity due to changes in position within a given velocity field. This is because of non-uniform flow. So because the velocity is not the same everywhere. So this would be like flowing through a nozzle. So you come in with one velocity, you go and move to a different location, and now you're going faster. Local acceleration, that's a change because of changes in the velocity field. So that's unsteady flow. So that would be like turning on a hose. So if you're the water in the hose and somebody opens the valve and turns you on, you're accelerating because somebody's turning on the hose and things are changing with time. So that's what this last term is. So typically when we've done things in this class, we've only looked at situations where that's not happening. But in general, it could be happening. So we'll keep it there. This last part, this guy, capital D V dt, it's like a differential, but we give it as capital D because that makes us feel weird when we look at it. Because we always look, differentials are small d's, and maybe sometimes they're like leaning over funny looking d's, and sometimes they're squiggly d's, but they're always lowercase. So we give it this weird capital thing because it's to give us like, a pause. This is not a normal differential. Don't treat it as such. We call it the material derivative or the particle material derivative or the particle derivative. And really that's just to connect, right? It's the particle derivative of the velocity field. It's basically to say, how does or what is happening to an individual particle, an individual fluid particle, or an individual piece of material in that velocity field. So how is that changing with time? Its definition, you probably won't run into it that many places, but you may run into somebody talking about the particle derivative or the material derivative. So that's all that it's talking about. It's how we're connecting what's happening to a particle to what's happening like in the broader picture, the broader flow. Another notation way of writing it, which is again the same thing but a little bit more compact. We could write that the material derivative or the particle derivative is equal to velocity dotted with the gradient. So the velocity gradient times the velocity plus the change in velocity with time. So this is an equivalent way of writing the equation that we wrote a little bit ago, just a little bit more compact. Velocity gradient times the velocity plus the change in velocity with time. Okay. All right, so let's try to think a little bit, and we'll end on this. So let's think a little bit about what the material derivative is. And we'll do this by picturing yourself as a little T-Rex flying an airplane. So a very, clearly a real world example. Okay, so we're going to picture this because we'll be thinking about this in terms of temperature. And that's because temperature is not a vector, so it makes it easier to think about. So what you want to know as the little dino flying an airplane, you want to know like whether you need a hat and gloves. So you care about the temperature at your location for yourself, right? The T-Rex has little tiny gloves. He's got these little baby arms. You probably wear like person gloves. So you care about that, right? I don't know if they make hats big enough for T-Rex, but maybe. You can draw a little hat in them. Somebody with more artistic ability than me. Okay, so you're the T-Rex. You care about what your temperature is at your present location. You have two pieces of information. You have a weather report, and you know how fast you're moving and in what direction. Okay, so how are these things connected? So the weather report, that's like we would call it the temperature field. You know how the temperature changes spatially. It changes, in this case, we're going to say it changes as you go north. How does it change as you go north? It changes every 5 miles that you travel north, it changes by 1 degree. So it gets colder 1 degree every 5 miles. You know that from the weather report. The other thing that you know is how the temperature changes as you go up. So you know that every 1,000 feet of elevation gain, the temperature goes down by 3 degrees. So that's this part. So that's telling you how temperature is changing spatially in the world. And what you know is how you're flying and how you're moving spatially. So you know you're going 300 miles an hour north, and you're also climbing 3,000 feet per minute. Okay, so you know your y component of your velocity, how fast you're going north, and you also know the w component of the velocity, how fast you're going up in the z direction. So we can use the material derivative to figure out how fast the temperature is changing for you in your airplane. So that's going to be we'll do the material derivative of the temperature. That equals partial t partial x u plus partial t partial y, little v plus partial t partial z, w plus d temperature d time. Okay, so this would be the material derivative of the temperature. This component here, the change in temperature with time, this would be like, no, not highlighter. This would be weather changes, like the temperature everywhere starts changing. So that would obviously affect you no matter where you are. So that's if the weather changes, okay, sure, your temperature is going to change, right? As it goes from, morning to the middle of the day, the temperature is changing because the weather is changing. These other components here are changes in temperature because you're moving from one location to a different location. So you're not moving in the U direction. So you're not moving east or west. So U equals 0 in this specific example. So the temperature, the time, that's how fast is the temperature changing as you go north. So that's going to be -1 degree Fahrenheit per 5 miles. And how fast are you heading north? You're heading north at 300 miles per hour. Okay. So that's how your temperature is going to change because you're traveling north. Then the second part, your temperature is changing as you go up. So that is -3 degrees Fahrenheit per 1,000 feet. And you're climbing at 3,000 feet per minute. Okay, and okay, the weather's not changing at all, so that part's 0, plus 0. So we can look at U, the temperature change for U, that's the material derivative. How that's changing with time, that equals, this would be -60 degrees F per hour, minus, okay, so 3,000 times 3 divided by 1,000 minus 9 degrees F per minute. So the temperature is changing 60 degrees every hour because you're traveling north, and it's changing 9 degrees every minute because you're going up. So at this instant in time, the temperature, the time equals -10 degrees F per minute. Okay, so that is for you, this is an instantaneous value, right? So this is how fast temperature is changing for you as you're sitting in your airplane. The temperature is dropping 10 degrees every minute. As you move to a different place, the temperature field could change. So maybe you go, you head a little bit north and then the temperature starts going up again because it's warm and sunny further north. So then the temperature field could change depending on your location. But this is giving you an instantaneous temperature change. So this handles the acceleration term. Next time on Monday, we're going to do mass and force, and then we'll have F equals ma. So it should be fun. Hope you guys have a good Friday, and we'll see you back here Monday. Enjoy the weekend.